Hello at all. Welcome to our joint webinar of Emproof and Swissbit. Today we would like to talk to you about embedded firmware and what you can find in firmware. As a guest speaker today we have Roland Marx from Swissbit. Roland, do you like to introduce yourself?
Yes, maybe just one quick thing. So at least in the online stream I don't see us yet.
That's fine. We have a 1 minute delay.
Okay, then that's fine. Yeah. So welcome everybody. So I'm Roland from Swissbit, and I'm also part-time hacker, consultant, and so on, and do a lot of things with embedded Linux devices, and will tell you some insights of what you can find there and how you can protect it.
Okay, so the webinar today will be two halves. The first half will belong to Roland, where he shows you about embedded Linux stuff, and then later on in the webinar I'll join into the bare metal firmware stuff. So let's start. The screen is yours, Roland.
Okay, so I hope everything's on, Tim?
Yes, fine.
Okay, then I will start. So, what will I talk about? So, as I said, so I'm doing embedded cybersecurity stuff for a long time on different not sides, but with different perspectives, I would say. And some of the things I can tell you here. Right now I'm with Swissbit, and here I'm senior product manager for our embedded flash storages. And so I will tell you a lot of things like what is about these flash storages and what can you do to protect, and why are they maybe weak, and what should you do, and what should you consider if you want to make a IoT project public, for example, and what is on it. And also a very recent topic is Cyber Resilience Act and Radio Equipment Directive, and this is all about cybersecurity of these kinds of products. So I hope you can take some ideas with you what you should consider in your risk assessment, and maybe even some countermeasures. Allow me a quick introduction of what Swissbit is doing. So roughly saying, Swissbit has been doing industrial flash memories for 20 years. We also have FIDO sticks, like something you might also know as YubiKey. Yeah? So these kinds of hardware security tokens we also have. And the cool thing about Swissbit is that we produce our flash in Germany, in Berlin. And roughly the block diagram of such a flash device looks like this. So you have the real physical flash, and in between the hosts, so here on these golden contacts and the physical flash, you always have some kind of embedded microcontroller. And in our case, this is the Swissbit or Swissbit owned flash controller, where we own the hardware IP and the software IP. And on top of this, we can even additionally add a secure element, so a real certified secure element for private key storage and so on inside of such a small micro SD card, for example. And with these things, we can do very interesting topics. So our built-in, or maybe just to state this, so because we have this hardware IP from this flash controller, we also can control its firmware. And this is why we add some more security features to our cards that normally nobody else is doing. And with this, for example, we can protect drones or body cams, so that whenever you go to such a cam, or you find one and you try to look at the card, what's on it, you will not see anything, or you will only see AES encrypted garbage that does not mean anything to you. Or at least in Germany and Europe, you have very likely seen a signature on a cash receipt. This is very often digitally signed by some of our products. So everything done automatically inside of a micro SD card. And the point of sale system itself does not need to do very much about that. But we also have solutions for embedded systems like Raspberry Pis or industrial computers, and with different scopes. So and because I do take care of the security of these kinds of devices, I want to give you a little insight, or maybe also a shifted perspective on what you can store on these things, but also how you can attack these things. So let's have some ethical hacking use cases first. I'm not sure who is here and already has used the Raspberry Pi, but I guess that many people from time to time have this problem. They pull out a Pi or an old micro SD card, and you try to log in, and then you see, wow, I cannot log in. Did I use a wrong username, or did I use a different password? Yeah, what should I do now? And so to know what we could do here is to understand first how Linux systems are storing passwords. So, and also I think I need to go out of the way. So in Linux systems, you have the so-called password file and the shadow file that are located in the directory etc. The password file was used before for storing passwords, but this is not done anymore. Currently in this file, you only see like the username, user ID and stuff, and which shell this user is using. And the real password is more or less indirectly stored in the so-called shadow file. And an entry in the shadow file looks like this. You see username, you see some dollar number, some salt, so some random value, and then something looking like a hash. So it's actually not really the password that you typed in, and then some metadata. And as you can see here, so this $6 means in this case, it's SHA-512 to use for this hashing. And the salt value is some random value that only the system is knowing, and is also generating it by whatever reason when this user is created, or maybe at system startup. And then the password that I type in will never look the same, so no matter whether I type it in this first or second computer. And so far, so good. So actually, nobody can easily retrieve this password. Sure, there are also tools to do this, but let's take for the moment that this is not very easy. And okay, but now I know where my password is stored, and maybe I am user John Doe. So what can I do to gain access again to my device? So on the left side, this Alice Pi. This is the Pi where I don't have the access at the moment. So what I have to do is I have to remove the card. I have to mount it somewhere, maybe in a different Raspberry Pi. Then I can run a script or do it manually so that I change this shadow file. I patch the name of, I patch my hash that I know from a password that I know and put it in. And then I restart this Raspberry Pi. And after that, I can use my new password. And also the old password is not working anymore. So this is the only thing. In this case, this could be detected for sure. But at least I would have access. And just by pulling out the card using some random Linux computer, changing a little bit and put it back in. So the protection of this password is very weak because we had physical access to the storage medium. And I also did some small script that can automate this task. So it's actually not much, as you see here. It works like this. You just have a certain mount point and want that the card is automatically mounted whenever you enter it. And then it asks you, hey, which username do you want to patch, like to change the password, and what is the new password? And then here actually, where is it here? The SED is doing this actual patching and changing the content of the file, and afterwards it should run. So actually, I did not really check this. I had some scripts, but this was kind of a backup of ChatGPT that I used just for showing the rough purpose. And also, you can even automate this more. So you can have a certain list of usernames and then automatically patch it and directly say, okay, I'm done. Then you can pull out the card and everything's fine. So this can be easily automated. So this was like one attack, or actually kind of circumvention for my own Raspberry Pi where it's okay. But if it would not be my own Raspberry Pi or not my own IoT device, then I think this would be an attack. Another thing is like no backup, no compassion. So in German you say kein Backup, kein Mitleid. So let's have a backup, because if in case maybe something is broken, I can recover. So what should I do backups of? And we will have some additional examples later. So everything that I want to back up is normally the part that is not the open source software, because this can be easily rebuilt or redeployed. But my configuration files, my user data, my logs, everything that is valuable to me, and actually this is the asset that I should protect later. So I can do a backup of it. I could also just dump the whole card. That's not an issue. So you can easily make a backup of a whole card. I think 23 gigabytes takes 10 minutes, and then you're good. You can put the old card in, and that's fine. But you can also just say, I take only what I need. And how would this look? Very similar. You go to the device, you pull out the card, you mount it in a different device, you run a script that does a backup. You insert the card again, and in this case we did not change any file, so the system would run like before. And also in this IoT use case, you can see, so the system, let me have a laser pointer. So the system, for example, would connect to a backend system, and this would still work. But very likely, my clone, if I would just clone this card completely, my clone would also be able to connect to the backend system. And the biggest issue here is the backend system might not really differentiate whether so my clone or the original one was the original device. So this is a real issue for IoT devices. And there's only hardware security that you can do, like really having a secure element, kind of a TPM, HSM, or our security level 3 cards that have such as real private key storage, where you can prevent the copying of this private key that you normally use for TLS connections. Also, again, a small script that can just help you to do a backup of your most essential files. So you can make this list as long as you want. So actually this thing is just checking whether you want to do a full dump or a partially backup and so on. And then it's also waiting for the SD card, and whenever the card is in, you can you get your backup dumped. And also, I think I had some also other versions of the script that's just counting the time, and it was in the range of a few seconds if you just consider only the small text files that are important for you normally. So if it would be in a security audit, then what would we say here? So actually the system is fully compromised or compromisable, because all data is always visible. All credentials can be easily cloned. You have no integrity at all. So I could also not just change the password, but add my own applications. As we also later see, so also I could change the DNS settings or something else. So I will reroute the traffic through my maybe logging server or whatever. So there's no security really doable in such a system. And it's very easy to do. So the experience level is very low. Attack vector, this is the only good thing. You need to be physically near the device. So otherwise you will not get the access to the card. But if you can do this somehow, then all the rest is very easy. Detectability also, I said, medium or low, because it does not take much time. It maybe only takes a minute or less. And also the tools that you need, like Raspberry Pi, whatever, are very easy to get, or everybody has such a thing already. So this was SD cards. Many people say, okay, but I use eMMC and they are not so easy to pull out. Yes and no. So SD cards and eMMCs are more or less similar things. eMMCs cannot be taken out directly, but you can also easily desolder them. So if you have one device with with reasonable assets, it's not a big thing to pull it off. Or also normally for your own maintenance, for these kinds of devices, you have some kind of a debugging adapter or USB connector where you maybe need to set some jumper wires or whatever. But then normally you also get direct access to the eMMC. And if you have that, then also you can do the same things like if it would be a card reader. So also in this USB case on the right, so it would just be visible as a card reader. Maybe you would need a driver or something like this, but that's very, very similar. So let's have a more generic look. So we've seen 2 or 3 examples, but there might be many more things. So if you consider industrial projects, you might have credentials in all kinds of forms, API tokens, whatever, or even private keys that are normally also stored or can be stored in file systems, that give you access to some server or identify your product, or give you the right to use a certain software like a license. Many things, also privacy related things like GPS tracking, videos, camera data, audio files, whatever. All these things will be stored on such a storage device, and if it's not somehow externally or different way protected, then it is completely at risk. So, okay, so some animation problem here. So let's have a detailed look into some other examples, like what more critical things you might have in Linux systems. So one thing is everything related to SSH, so remote access. So there's, for example, the SSH config, which tells if it's allowed to log in as root, whether I can use passwords or only public keys. And if this file can also be changed, like my shadow file we've seen before, then I can also change the whole access to this device. And also, I think very tricky is this authorized keys files. So every user can create a so-called .ssh authorized key file, where you just put some public keys. Yeah? So it's not really critical. You put public keys in here, and the owner of the private key that matches to this public key may log in. Not very dangerous as this sounds, but if I, as an attacker, would just add one more line here that looks totally similar, and I think no human eye might see this, then I have kind of a backdoor user account here, or a public key account. So it would not be recognized as a separate user. It's just the normal user, but there's just one more key that might give me access, and nobody might check that. Yeah, so this is also a file where you should really look at. As well, yeah, for sure. I just called this ID RSA. So this is the standard name if you create a SSH key. Yeah, so you should create the keys like with a good name. But this is just one example. And if you have this key on your file system and you don't use a passphrase, which normally you are asked for, then the attacker can directly use this key. For IoT systems, very often they don't have a passphrase because they need to automatically log in. Yeah? So if they need to do this with a script, then the issue is nobody can type in the passphrase. And if you have this passphrase in the script itself, so then the security would not be better. But here there's a critical thing. Yeah? So these keys should be placed not on the file system, they should be placed on private key storages. So what else do we have? Okay. So I cannot do all the examples, but let's have this one, for example, also. So if you do a TLS connection with your with your web shop or whatever, chatting system or whatever, you normally the server authenticates itself by using a TLS certificate. And this certificate will be then checked by your computer. And for this, it needs to have at least one root CA from which all the certificates can be derived from. And if I, as an attacker, want to fake my website, so that I say I have Amazon.com, for example, then I can just put the right root CA into this folder here. So etc SSL certs, and add my own root certificate that trusts this fake Amazon, and nobody would really care. Yeah, so this is also important to understand that also these kinds of things can happen. So it's actually not really getting out your secrets, but giving you something in, and then maybe some security mechanism might not work anymore. Also, like Wi-Fi configs. Yeah, so here this is just one example for the WPA supplicant. So here also the password of whatever client network you are in is stored on any Linux system as plain text. So this cannot and is not encrypted. And also, so I just checked out because I didn't find my config. So I'm having a newer Raspberry Pi with Debian Bookworm, and so there it's using Network Manager, and here it's even easier. So every connection is found in the folder System Connections, and also here it's the same. So the SSID and the keys are just stored in plain text. Here for weak password for my hotspot, I just created it like this. Is this so there are many more things like privacy topics like browser passwords, history, and even the bash history, which I will show just one slide after this. But also logs might be interesting. Yeah, so the authentication log to see when an attacker got access. Yeah, so this should normally not be tampered with, or the routing or DNS settings, firewall settings, and as I already told, like cloud connections, but also more and more AIs or AI files, models, and whatever, or databases that run on certain devices that can be dumped directly, or at least I have the access to it. And this bash history I found very interesting. So a friend of mine got me a hint. So he found a post, said, "Good Lord, I pulled out a micro SD card out of a Raspberry Pi inside an IoT product." And it happens they had some developer use a Raspberry Pi to develop or test that code. And then they just yanked the SD card out of that machine, made a copy of it and deployed it to their products. Yeah, and he found a bash history file where you could see many things that this user did. Yeah, and also like private repos and so on. So this SD card, so actually I would not even consider this as a hack, because actually there were like circumventing security mechanisms, because there were no. Yeah, so it was kind of very easy to read out. As my time is almost over, or it is actually, so I just want to give you one hint what you can do against that. So and also this is the part where I do some little product placement. As I said before, we have this cards and we have this Swissbit owned flash controller, and with this it's actually like if you had another like gatekeeping controller before your micro SD card. And here built in we have an access control feature where you can say for each partition whether it should be publicly readable like it normally would be on any card, or whether it should be private. And one extra thing is also that you can set it to read only. Yeah, so you can have like integrity protection of some files like your SSL, root CAs, and can say, hey, nobody is able to touch this. Yeah, it is prevented by our flash controller. Even if you have root access, nobody can do this. And this is a mighty toolbox which you can use to even do secure boot on a Raspberry Pi. This is also something that we have on our website. I cannot show too much in detail here, so it's just so we have some kind of these diagrams, and I explain everything in some videos. Unfortunately, I will not do it here in the video, and will also give Tim the time to explain, like not on the Linux level, but lower level. So if you have really like smaller devices, what you can do there. Yeah, thanks for watching, and I'm happy to hear some questions later.
Thank you a lot, Roland. So let's do a small recap. So what we talked about is embedded Linux, and embedded Linux basically has some hard-coded files like SSH key, the passvd file, and then Wi-Fi configs, and so on and so on. So a lot of things that Roland just introduced. And embedded Linux usually runs on everything which is pretty small but still requires an operating system. So like Wi-Fi routers, IPD cameras, and so on. However, there are also things which are called something like bare metal devices. And bare metal devices is basically everything which does not have an operating system. So no operating system, basically. So what does it mean? So instead of having an operating system like a Linux, where you have a user configuration, user land, kernel land, and so on, what you do have is only a firmware blob. And this firmware blob directly communicates with the hardware and runs on the hardware. And in things like that, so this usually runs on small devices, like on sensors, on small microcontrollers, on drones, and on everything which is basically pretty small and doesn't require, or an operating system would be overkill. So a bare metal device, basically, or firmware, is significantly more low level than in an embedded Linux. And we usually have one large binary blob, which then is used to communicate everything, like communication to the hardware, executing the user account, and so on and so on. And today we talk about what actual information that might be potentially interesting or worthwhile analyzing are available on such bare metal devices. And furthermore, we'll take a look how we can extract them manually. So let me switch to some slides first. So question is now, what is in embedded firmware? And especially with the focus on deeply embedded firmware. And so basically everything which might be interesting to extract and might give you some context. For instance, hard-coded credentials of any form. So this usually happens that we see hard-coded usernames and passwords, for instance, for cloud infrastructure, because the device is phoning home and it needs to log into the cloud. Or also cryptographic keys, that we have hard-coded sensitive keys like an RSA key or an SSH key, but also symmetric keys for IAS and stuff like that. So hard-coded credentials are quite common in deeply embedded devices, and at the same time they can be easily extracted because they are in plain text. However, it's not always about hard-coded credentials like keys and passwords we are interested in. Sometimes we are also interested in learning about the context of the embedded firmware. Like, are there hard-coded domain names or IP addresses? This might also give insights about how the device communicates with other devices, or where to expect. Maybe we are interested in doing a web-based pen test, for instance, on some router gateway, and then we can extract the IP address of the gateway from the firmware. We also find a lot of keywords that reveal the context in the binary, like are there any network protocols, what network protocols are used, what is the use case of the firmware, what does it support, and things like that can be extracted just based on some keywords. And finally, there again might be real intellectual property, like algorithms which have been developed with years of research and are implemented there to do some analysis or to do some file parsing or whatsoever, and this secret IP should not be revealed. Here, we can basically, as you will see in a few minutes, we can easily find things in the binary and get at least a high-level understanding about what the code is doing. So let's say now we have some expectations what might be in there in the binary. Let's take a look at one concrete example. So what we'll have here is a small file. This car demo file, and if we take a look at it, we will see that this is an ELF 32-bit file for the ARM 32-bit architecture. So what this basically tells us is ELF means for executable linkable file format. This is a firmware file or an executable file for a 32-bit architecture, namely ARM. So we basically have somewhere some ARM 32-bit microcontroller, and this file contains all the code and data that runs on the device. Okay, we now know that this is a file, but we don't know what to do with that. So let's say we want to learn about what might be potentially in there. One thing we could do is just use the strings command first. The strings command is basically a command. It's basically a command which allows you to showcase, to search an entire file and extract all ASCII strings. And these ASCII strings, as a standalone, often reveal context. So let's take a look at that. And if we see, there are a lot of things which we don't know about, but still there are other things we might be interested. So, for instance, here we see GCC for ARM embedded processors. So here we identified the compiler which the code has been compiled with. It's the GCC compiler. Then we see something like TP-Link 7080. So this is usually some form of router. We don't have any clue why this is in here, but as we can see right now, there's some string called TP-Link indicating a router. There's also a string called elephant, which I don't know is used for somewhat. Maybe you will find out later. There are other things. Here we see something like Arduino. So just by looking at the strings, we can learn that this might be some Arduino-based microcontroller. Then we see something as Wi-Fi. So maybe there is Wi-Fi support included in the binary, which might again also work up with that we see TP-Link here, but we'll see. Then we see something like private var folders. So we have a hard-coded file in here, of a hard-coded file path. Then we see a lot of potential errors. And then we see AT, client connected, AT, begin server, server write. So this seems to be related to some form of network communication due to the connected and AT plus and so on. Then we have more of that, like host name, host by name, and so on. Then we have connection, user agent, host, HTTP. This looks, compared with something like get, start, exploit, IP, unprotected, this looks like a typical HTTP request. Then we see Emproof robot version. Maybe this is the firmware of a robot. We also see something which looks like an IP address. And we get some far more information. Here we see some HTTP headers. We again see some file paths. And I think that's most of the interesting stuff. So we can conclude that just by looking at the strings, we can find a lot of information. So based on that, what did we already learn? So what we learned is that we have some Wi-Fi related. That this is an Arduino. It's compiled with GCC. Then we also learned that we have a hard-coded IP address. We have a hard-coded IP address. And then we also have some HTTP requests. And that this is something like a robot. So these are a few things we just learned about the binary, about the firmware, just by looking at the strings. Because we can look at the strings and identify common keywords and then put them into context. And so we might think we have a hard-coded IP address, we have something Wi-Fi related. So maybe we have the the robot firmware connects to a Wi-Fi and then contacts some hard-coded IP address and performs some HTTP communication. This might be one educated guess only by looking at the strings and the functionality. But is there a way that we can learn more about that besides just looking at the strings? And yes, we can. This is something which is called reverse engineering. I won't go into much details here about reverse engineering today. However, I just want to showcase that we can use free tools like Ghidra, which allow us to look in the binary. So we can analyze the binary and then have a window here which allows us to see an approximation of the high-level code. Like, it's not the original high-level code, but it at least showcases us that we can learn a few things about it. So, for instance here, we can see the same strings we saw before. For instance, let's look at this TP link. So, and here we see that this TP link is somewhere placed in the data section of this firmware. However, Ghidra is more powerful. It does not only allow us to see which strings are in there, it also allows us to see how these strings are used in code. And therefore, for instance, we could go to code locations like this one, and here we see this is low-level assembly code. We don't interested that much in that, but we see that this code somehow uses this TP link. Now we can take a look at the decompiler output. The decompiler output is basically the approximation of the high-level code. And then we can see something like a string here with communication with Wi-Fi module failed. So we already have some context. We are in somewhere during Wi-Fi communication. And then, like, please upgrade firmware. And then we have a string that tells us attempting to connect to network named some name. And then we can see here is our TP-link string again. So, and it tells us that we try to connect to a network named and then TP-link. So an educated guess might be that this TP-link underscore 7A0 might be the SSID or the network name of the Wi-Fi the robot tries to connect to. And what happens? Usually, if we try to connect to a Wi-Fi, we have to somehow provide a password too. And so, if we take a further look, we see that we do a function call to this function and see that not only the SSID is given as a parameter, but also the string elephant. And this then is most likely the password. So, by looking at some context, like the Wi-Fi and how the strings are used, we can do more educated guesses that, hey, if we try on to authenticate at a Wi-Fi and we provide the network name, we might also provide a password. And then we see something like elephant, which is most likely the password of the Wi-Fi. And by looking at that now, based on the embedded firmware, we extracted the SSID and the password of a Wi-Fi. And now we could use this knowledge to connect arbitrary devices to this Wi-Fi as long as we are near to this Wi-Fi. This is one example how we could identify interesting secrets in low-level embedded firmware and uses our advantage. Maybe here are also things included like credentials for network-based authentication or cryptographic keys or something like that, which might be used in a different context. So we don't really know, right now, but these might be things which we could use. So there are some other strings that we could take a look at. For instance, here these IP addresses or these network commands, but I will stop here just to showcase that this was just one example that we can receive some information. The question is if we could do anything about that, and the answer is yes, we could. So there is a technique called anti-reverse engineering techniques, and anti-reverse engineering has the goal to more or less prevent the analysis. The idea there is that we hide, that we encode the data, that it's not stored in plain text, and at the same time encode and at the same time make the code more complex to analyze, such that an attacker has to do significantly of more work to analyze what's going on. There are also active protections that prevent the debugging and the patching of the code, like anti-debug and anti-tamper, which not only prevent reverse engineering by looking at the code, but at the same time they ensure that you can't attach with the debugger to the device and single step the instructions or patch the instructions and something like that. In the next time we will do a more dedicated webinar based on these things. So for now it's just important that there is something like IP protection, like anti-reverse engineering techniques that allow you to prevent doing something like that. There's also a small demo I would shortly demonstrate. So you can do it in detail later on at home. So for instance here we have an IP protection demo where we could have some simple source code like RC4, some cryptographic algorithm, which would be stored in plain text here. And what we could do is, for instance, we could say we want to compile it first, and then it's compiled in the background. And here we would see the assembly code, which would be things that we saw before. We could also look at the decompiler output and see the high-level code approximation as you've seen it before. And now we could apply a technique called code obfuscation. And if we do that and apply it, for instance, with our tool Nyx, once we've done that, we get a protected code for which we don't easily see anymore what's going on, because we only can partially recreate things. So, and this is a technique called anti-reverse engineering, which prevents or impedes analysis and makes it significantly harder. So to conclude, that embedded Linux systems, but also bare metal devices, often contain sensitive information in the embedded firmware, and there are techniques to impede the analysis, like for instance for the low-level part, especially something like anti-reverse engineering techniques, which allow you to harden your code. And if you would like to try it yourself, I can encourage you testing out the demo on your own and also playing around with the binary. So the binary will be released later on, including with recording of this webinar. And if you take a look at some of our prior recordings, we have 101 how to reverse engineer embedded firmware with the Ghidra. This is one of the other webinars. So this was the part from my side, and thanks a lot. Thanks also to Roland, and now we are open for questions. So, do you have any questions? If so, feel free to just write it in the comments.
Exactly. I also already have written it there. And wow, that was a nice look into the tube. Okay, I think currently, Tim,
yeah, we have
you also
delay,
don't see any questions, or?
But maybe I have a question for you in between. You showed us this product to harden the SD cards. Is there any way how we could test that or retrieve that? So what should people do which are interested in this technology?
So you mean like how secure is this security mechanism, or
no, how they can test it on their own? So if they like what they saw, how should they get their hands on that?
Yeah, so actually this technology is existing quite long, but nobody really knew about that. And so if you go to community.swissbit.com, then you can find a lot of tutorials, videos explaining how is it working, what's like how is this also the state machine of this protection mechanism. Because also it can be reverted if you want. So there's a lot of explanatory material, and the devices you can buy them. So we are still in the product launch phase, but there are some distributors where you can buy it already. Amazon will also follow, but you can buy it at Rotronic, Alnet, Mauser, for example, but also others like DigiKey. So we are just shipping to all the normal main distributors that we also where you would also find Swissbit products normally.
Okay.
And so because it's Christmas, maybe so if anybody is writing a nice comment and wants to have one kit, I can also arrange some free sample shippings, but only for the live recording.
Okay, there's the question, does this obfuscation also protect against fault injection? The short answer is no. So fault injection is typically another attack vector where you would need something as anti-glitching or something like that. However, code obfuscation implicitly can help there by making the code more harder to analyze, such that the attacker has a harder time figuring out where the glitching could happen or where the fault injection should be done. So implicitly a bit, but against the real attack, not really.
And yeah, then also I would have another question, because I've seen an obfuscation talk also lately, as you know, and there also one question was, how can you somehow prove that whatever you have obfuscated is doing the same stuff as it did before, and maybe you did not include some backdoors or whatever. So I think you're changing a lot, and it's very hard to link the binary afterwards to the code base or to the requirements. So how is this normally handled? So do you just do better testing and see that it's like a regression test, that nothing changed, or also the performance loss or something like this?
So in general, yes. So the idea of code obfuscation is that it does not change the underlying semantics, the underlying behavior of the code. It just adds extra layers such that the code looks different but computes the same. So, and the question is how to ensure that. Well, you can do some form of mathematically proving informal verification for smaller parts that they behave the same, but in the end, for large-scale verification, it breaks down to a lot of fuzzing and random testing. Like you apply it to a lot of different complex binaries and functionalities, and compare with random testing and fuzzing that the original and the modified version behave the same. And the larger the test scale, the better the chances that nothing breaks.
And how about the file size? So is it dramatically changing? So like, what is the overhead by this obfuscation?
This also highly depends. Like if we are on the desktop area, you usually find something like factor 100 to factor 500. On bare metal systems and deeply embedded devices, there's by far nothing what you can do there. There you only have a few kilobytes or MBs of ROM, where you only can do like up to 10% overhead. So, and this is where, for instance, we at Emproof are specialized in, that we take high core security and break it down to deeply embedded devices with low overhead constraints.
Mm-hmm. So, but in general, like if I would allow more overhead, then it would make it also harder to reverse engineer, or because I could do like much more.
Yes, that's
like
absolutely
nonsense code.
Yeah, the more you can, the more space you have, the more you can do. That's always the case.
Yeah, okay. Yeah. Also, I found it really like the things I was talking to about was like really. I would say low level, so kind of easy attacks, yeah. And I just did not even look into the code, yeah. But at least if I was thinking like if you have it, if you make it so easy that your application or maybe your license mechanism is lying on an SD card and unprotected, then also maybe one thing could be obfuscated with your tools, yeah. And then at least. This is also much harder. Yeah? So at least this was an idea, but this does not work, for example, for Linux config files, because you cannot obfuscate them. The Linux system needs to read them. But at least for applications, you could do a little bit.
True. And especially on the SD card example, if you can access the entire system, you can extract a lot of valuable information, which might allow you then to forward to network device to other network devices, cloud devices, and so on. So yeah, lots of attack potential you can do if you don't protect them.
Okay, so I see two more questions.
I see some. Yeah, some is what are the storage sizes of the secure SD card? What about the costs?
The cost is roughly, so the retail one-piece cost is roughly, I think, below 40 euros for the 16 gigabyte version. But I also have to tell that this internally has 60 gigabytes, so we have a lot of spare flash for robustness and redundancy. So this is called PSLC mode that we use this flash in, so it lasts much longer. And so these are the rough costs. So it is more expensive for sure, but it's also having a lot of other benefits for safety and security.
Okay. There's another question. Can you share information related to aviation security and satellite security? Is this related for you, or shall we answer?
So I would guess that this might be something like safety and code, and I think this could be more like for you, but because I could think so. If you write avionic code, then everything is double and triple and quadruple checked, and also the test results are checked. So I'm not sure if it would be allowed to obfuscate in these cases. But maybe you have some examples.
In these areas, safety, functional safety is pretty important. That you have standardizations that you don't, and certification that you don't break things with your code transformations. That's, by the way, something we have for the automotive area. However, also about related to security, especially satellite security, there has been some papers in the last years from the Ruhr-Universität Bochum about satellite security, where they came to the conclusion that it looks like the 90s. It's a lot of exploitable buffer overflows and so on, not much code protection. So yeah, satellite security, at least in some areas, is not that much advanced as one would think it should be, but yeah, there are further resources that you can find online.
But I think it might be hard to get a binary from a satellite.
Yeah, exactly.
So, at least remotely.
Exactly. There's another question. is there a protection against QEMU emulation? It might be easier to deobfuscate during execution. Yes, so basically QEMU emulation is basically the idea there is that you use emulation to emulate the code and analyze its behavior. And there are techniques which are similar to anti-debug or anti-tamper, which are called anti-emulation, which basically work by introducing faults into the code that is known that is handled wrongly by QEMU or other emulators. And with something like that, you can fool emulation. So yeah, something like that exists and is actively and is very common. There's another question, I think, for you, if there are any samples to try out.
Yeah, just get in touch, I would say. So private message and refer to this webinar, and then I can arrange stuff.
Okay.
But also one question from my side regarding this QEMU. So this is only for the Linux kind of devices, or is QEMU also doing simulation for bare metal systems?
QEMU can also emulate bare metal, yes. Like Tricore, for instance.
Okay, so if there are no more questions.
Okay.
I enjoyed it. Thank you, Tim, for the chance to do this webinar together again.
Yeah.
And let's hope that the recording and everything is working. And yeah, wish you a nice day, and thanks for watching.
Thanks, you too. And yes, have a nice day. Goodbye.
Bye.